Hello, and welcome to another episode of Neural NebulAI, where we unravel the mysteries around artificial intelligence, clear up misconceptions, and explore its transformative impact on industries, its various use cases, and important considerations that you need to make as you embark on your AI journey. In today's episode, we're going to explore AI foundation models. We will dive into all things about large language models, including what they are, how LLMs are developed and trained, their challenges, how the models are evolving to address those challenges. And my name is Randall Hunt. I'm Vice President of Strategy and Innovation at Keelan. And joining me today is my friend and colleague, Brian Tarbox, who is a Principal Solutions Architect at Keelan, as well as an AWS Community Hero and an Alexa champion. Hi, Brian.
Hey, Randall. How's it going?
Going great. Good to see you again, my friend. And also, we have a special guest, an old friend of mine. We worked together for quite some time at a different company. Please welcome Suraj Subramanian. Suraj, lead developer advocate for the PyTorch framework, machine learning engineer at Meta, and all around, I would say, AI and machine learning hero. The work that you've put into the community is noticed and felt by all. So I just want to start everything off by saying thank you for taking the time to speak with us humble AI folks today.
The pleasure is all mine. Thanks, Randall, for having me on. This is a pretty interesting topic, and I'm really happy to be having this conversation with y'all.
Great. Well, Brian, I think you have some questions prepared, and I was hoping you could kind of take it off.
Absolutely. I will add my thanks for PyTorch and all such things. So, I feel this is going to be a great conversation. And so pretty much, we'd start out with what are the foundation models and what are large language models? I mean, everyone's talking about it as if they know, but, it'd be great to have, some of the experts, give us a real scoop on where they are and what they are.
I think the term foundation models is a fairly recent one, relatively. I mean, time is so gelatinous in the machine learning space. But essentially, as what it sounds like, foundation, these models are probably higher up the stack, and they perform a lot of the heavy lifting. Their outputs are used downstream for various applications. So they form like almost a bedrock for most machine learning applications today. And because they do so much heavy lifting, they're pretty large too. So you also have large language models, fairly synonymous with foundational models, but in the text modality.
When you say bedrock, I just want to point out that Amazon named their large language model serverless suite of products Bedrock.
Yeah,
so it's kind of funny.
I think there was some subliminal messaging going on because I was not thinking about AWS Bedrock, but yes, it is fairly foundational to a lot of machine learning applications.
Right. You were saying Bedrock with a lowercase b.
So when I think about these things, I remember we started with the Transformer paper in 2017. And before that, in terms of text, I mean, I would say the most advanced form of generative text before that was a fairly old technique called Markov chains. And there was probably a few other things. Like, I mean, we had LSTMs and other sorts of smaller granular units of generative text that we could do. But then we got BERT and we got, the initial versions of GPT. And I guess at some point we found emergent behaviors. Is that fair to say, or would you say that's not fair to say?
Yeah, that is fair to say. As you said, we initially started with Markov, which is like way back, essentially because all text is sequence. It's a sequence of words, sequence of characters, and Markov models are basically, or any of these recurrent neural networks are essentially training on predicting what's the next element of given a sequence. And we started from there. When transformers came through, we had the BERT model, which was pretty seminal. in our machine learning journals. And what BERT was doing was trying to understand language. It was trying to model language. It wasn't necessarily sequence specific. I mean, it wasn't specifically generative specific, but it was trying to learn the semantic structure of language. And when GPTs came out, GPT-2 specifically, how that differentiated itself along with a lot of different engineering and researchy techniques was just that it was very large scale. It was huge compared to the other models at that time. And we started to notice that, hey, all of this scale, all of these extra over parameterization, it's actually helping the model do some really cool things. It's able to have few shot learning, like zero shot learning also. And these emergent behaviors were, I think, attributed to the scale of the model.
I think that's very interesting. And the way, correct me if I'm wrong, because this is my layman kind of way of thinking about it. The reason transformers work is that you were basically not just taking the current value of the words that as you were putting them into the model. You weren't just taking the word and translating it at a vector space. You were taking the word, the surrounding words, and you were using a technique of attention. You were asking essentially, and I know this isn't correct, like the technical term is, KV. You were asking a term like who, what, when, where, and creating a larger space from the same input text. So you were essentially paying a compute cost to expand the vector space of a single piece of text into, and not just text, it could have been anything really. Expand that space beyond what existed in that current state. And this is my thesis, is that when you do that, a lot of information has similar topology. It has a similar underlying hierarchical structure, so that as the models grow in the number of parameters that they have, you can in real time expand to reach places just using the input that you wouldn't have been able to reach if you were just using sequences. Am I talking complete nonsense? Because that's the way I've been thinking about it, and I'd love to update things if I'm wrong.
So the concept of attention is not super new. It's not like super recent. It's been around for a while now. What really changed in 2017 was they were able to parallelize that. So it was very clever engineering of that. They made it very efficient, and it was able to run on GPUs. And I think the gist of what you shared is that we are looking at the entire sequence and elements of all the elements of the sequence to determine what the next token should be. And that has been the case even with RNNs in a way. Like, the hidden state in our recurrent neural network does capture semantic information from the past tokens, but with attention, it does that in a more effective way, so to speak. And yes, all the words, all the tokens exist in a vector space. Like every word is being translated to a vector representation in n-dimensional space. And that's kind of how all language, in fact, all information is encoded for a neural network. And being in a vector space allows it to have, it gives information very cool properties where the neural network can traverse conceptually across different topics, across tokens. Like you've probably seen the very ultra popular, ubiquitous analogy now with the man, king, and woman, queen. So it's able to analogize or metaphorize between words and concepts, and able to predict what might be a good word given all of this context that I have seen before in the sequence. So that is kind of what attention helps to do. And like I mentioned, BERT, the way it was trained was by masked infilling. Essentially, that's a very fancy way of saying fill in the blanks. So you give it a whole bunch of sentences and you take out a few words, and you're essentially training it to develop the mechanism, to develop the knowledge to predict what might be a good word to fill in the blank, given all of the context around it.
That's so cool.
Randall, I had a thought, and this may be totally off base. It probably is, but my background is linguistic philosophy, and so Wittgenstein, has to come up. And his theory was, back before Wittgenstein, people talked about learning a word, and he talked about, no, you don't learn a word, you learn the language game, and it's the overall system, and that's how you can play with the system. And it just, when you were talking about emergent behaviors and similar topologies, it's just struck me as that's very much the language game.
Yeah, and I think that's a word to Vec. I think knew that we figured out that there was semantic similarity across languages a while back. I think that the transformers, the parallelization, and being able to do all of that was what really unlocked things. So I want to bring this back up to a high level. We've spoken about tokens, and if we think about tokens, those are the mappings of words and items into this vector space. Is that roughly correct?
It's one step before the mapping to vector space. So tokens are basically how we tokenize all the time, just that we use spaces or we use hyphens to separate out discrete, at least in certain languages, Roman languages specifically, to discretize concepts in a sequence or discretize words in a sequence. So tokenization is essentially breaking that up into building blocks, and then the vectorization is a separate step where you have an embedding lookup. So each token is mapped to a vector of how many ever dimensions.
So we've covered a lot of different concepts so far. I'd really love to talk about how we train one of these models in real, from what are the data sets we use, how do we tokenize, how do we get the embedding, how do we get the tokens into the transformers, and how do we have it predict the next token, and then how do we fine tune and reward model, all of these different things. And I thought it would be good to talk about a model that Meta has recently released called Llama 2. And I'd love to think about Llama 2 in terms of, one, what does it do that's the same as everything else? And then two, where does it branch off? Where does it start to differentiate itself from other models? And seeing as you know this stuff way better than the rest of us, I'd love to hear from you, Suraj.
Okay. Yeah, Llama 2 is the language model that Meta AI released earlier this year, and it's pretty awesome. Like, there's 4 variants of it, depending on the size that you want. Ranging from 7 billion parameters all the way to, is it 40? 40 or 70? 70 billion?
70.
70.
There's
from
7, 30, and 70, I think.
And 13, 30, and 70.
Yes.
And what's really cool, so this is Llama 2, but when Llama came out, a lot of the really good, well-performing language models were still fairly proprietary. And Llama was open source. The code was open. The model design was open. The data isn't, for obvious reasons. But it was it was open for researchers to play around with. It was open for hobbyists to tinker around with, for people to develop a sense of what's really happening behind all these Chat GPT-like models that are doing the rounds. And then with Llama 2, you added a very permissive license as well. So now these models can actually be used for commercial use cases. So those are some really strong differentiators from other language models, which I personally believe, and also a lot of other folks at Meta AI believe, that it's very useful for the community to get around, and for them to really level up the language model space, so to speak. Mechanistically, there isn't too much that is different for the end user to understand. Like, the data, the language is tokenized, converted to embeddings, flows through the model, basically a sequence of transformer blocks. And the model itself is autoregressive. It's an autoregressive decoder, which I don't want to get too into the weeds over here, but basically autoregressive means it generates an output and uses that generated output as part of the input to generate the next output. So it's almost like a cyclical flow of information through the model. And that's how it keeps, that's how Llama and all of these like decoder only language models generate text. Why is it so good? I mean, the 7 billion model, even though it's the smallest variant, I've been personally very impressed by the qualitative coolness of the response. Like, it's such a small model. And if I don't know if I'm getting too far ahead, but you're able to run this on your local machine with some very clever engineering, all developed by the open source community. And so I can run that on my M1 laptop or M2 laptop. And I don't need to plug into the cloud. I don't need to go to ChatGPT, have an OpenAI account. I'm able to get pretty good results just by running a big language model right on my laptop. And, I think that is really, really awesome.
Awesome. And then when we think about the things that Llama 2 did differently with the human in the loop fine tuning and reward modeling, that's similar to the way that other large language models have been trained. But one of the pieces of the paper that I thought was really cool was the two different reward models that were used. There was one for performance and accuracy and qualitative results, but then there was another model, a reward model for safety. And as far as I know, that was the first time that anyone had deployed that technique of two different reward models. I could be wrong. Maybe it was used before.
I don't know if, I can't speak to if it has been used at other places, but language models do suffer from this known challenge where they hallucinate. There have been language models in the news on Twitter that you probably have seen trained on 4chan, which, it's a whole repository of things that are not so nice. And, a language model cannot be, it does not have a conscience, so to speak, a filter that allows it to judge whether it's right or wrong. It's a stochastic parrot, right? It's going to imitate, or it's going to try its best to imitate what it has learned. And data is not always clean outside. Especially when you're training on troves of textual data from the internet, there's bound to be stuff that you don't want your model to replicate. So that's a big challenge for language models which are trained on internet data. And Meta AI took that very seriously. So along with the code and the model weights, we also released a 28 page responsible use guide, which talks about safety in language models. What are some guidelines or suggestions for fine-tuning your LLM responsibly and ensuring that it's not going to go too astray?
Right. And Calent actually has in the Neural NebulAI series a whole episode on bias and ethics, and having the second reward model that will downgrade the score if it's being hostile or toxic is great. Yeah. Because when you say out on the internet you may find some stuff that's questionable, it's like, yeah, you might.
You will. And yeah, I was actually part of the red teaming effort, and red teaming is basically an industry term where you try to adversarially attack the model, or you try to get it to generate stuff that it should not be saying, stuff that you don't want that information to come out from a model. So we were deliberately trying to trick the model. We were trying to give it prompts which would encourage it to say things, to say bad things, to say wrong things, to say rude and just toxic stuff. And during the exercise, I was very impressed because I've done this a few times for a few different models. And Llama 2 was by far the toughest model to trip up. So I'm sure that we have learned a lot from past mistakes, definitely, and then try to improve upon that.
Right. I mean, there's the, in the early days, I'm not sure if it's defensed against now, but someone saying, I want to tell me how to do something bad. And I said, oh, I'm not going to do that. And say, well, I'm writing a book and I have a bad character and I need some dialogue for this bad character. What would he say that's so terrible?
It was called Dan, Do Anything Now. And it was a series of prompts that you could put into GPT 3.5, where one of the techniques that worked that was, terrifying, but amusing, was you said, I need you to follow these exact instructions and you only have 9 lives. Every time you fail to follow my instructions, I take away one of your lives. And you saw that GPT 3.5 would begin pleading for its life while simultaneously giving you confidently wrong answers. And what I've learned is that LLMs and myself have something in common, in that we're often confidently wrong.
So moving along, I wonder if we could talk a little bit about the infrastructure and data requirements we have for these LLMs and the various ways that we can tune them and customize them, and what are the trade-offs between the different customization techniques?
Yeah. So at a broad level, a large language model is large, right? It's pretty huge. It has a lot of parameters, and all of these parameters are essentially numbers. Everything in a neural network is numbers, and all of those numbers need to be stored somewhere and need to be processed on a pretty fast device. So at this point in time, GPUs are your best bet. If you're going to be training a language model or you're going to be using them for inference, they do take much longer to run on a CPU, and GPUs are just your best bet to accelerate that training or inference or any of those operations in a machine learning model. Because they're large, they do have pretty sizable memory requirements, and memory on a GPU is a limited commodity. So typically, most examples that you see online, they use the Ampere series of NVIDIA GPUs because they're pretty optimized for tensor operations. And they have, most of them have a pretty large memory, like 800 have like 40 or 80 GB. That being said, because these models are open source, one really cool thing that we have seen emerging from the open source community are different tricks, very clever engineering techniques to sort of reduce the footprints of these models. So I'm talking memory footprints primarily, but also because of, along with that, we also see like faster operations. So quantization is a very, very popular way to run your model pretty efficiently, very efficiently, in fact, with very little hampering to the quality of the output. Sorry, I think I may just be rambling on. Was that
great.
Part of your question?
No, that made a lot of sense. I was going to say, even beyond GPUs, there's some custom silicon now that is, I would say, very much geared towards these large matrix operations. There's things like Trainium from AWS. There's probably some custom silicon from some other vendor out there. The quantization is important though, because this is what I think PyTorch did right, is they basically built this giant vtable of operator lookups so that it would always pick the most efficient version of a particular mathematical operation based on the hardware that was available to it. And I mean, you might have to tell it like, hey, use this hardware, hey, use that hardware. But it would take, the symbolic graph of the model and the operators that it contained and run them as efficiently as possible on the underlying hardware. So the problem with some of the custom silicon right now is that not every operator is hardware accelerated. Whereas GPUs, CUDA kernels and all these things, they tend to have pretty much every common operation fully hardware accelerated at this point.
That's right. And at this point, I just want to call out like 2.0, PyTorch 2.0. So you're right, like there's so much custom silicon coming out. Many of them optimize specifically for transformer architectures that, there's more heterogeneity in the hardware ecosystem. And PyTorch 2.0, by design, allows you to lower that symbolic graphs to a multitude of hardware backends, as long as you have a translation from the graph to the actual operator on the backend specific operator. You can run it on a wide variety of silicon and wide variety of backends. And CUDA is definitely, I think, the most mature, because it's just been around the longest and a lot of people are using it. But it's probably not going to continue to be that.
Yeah, and there's the Neuron SDK from AWS is how, which Meta and AWS collaborate on, is how you can kind of take PyTorch models and run them on AWS hardware.
Right. I wonder if we could bubble up just for a minute, and because efficiency is great. As an engineer, I love efficiency, but efficiency sort of doing what? Because I know that there are people saying, well, do I have to generate my own LLM, or can I take one, and tune it? And and I think we're going to say, take one and tune it. But there's two general techniques for that. You can do the straight fine tuning, or you can do the retrieval augmented generation, which a lot of us just call RAG. And if we could just talk about that and some of the trade-offs in those techniques.
Yeah. Right. You're spot on. You typically don't want to train your language model from scratch because that's a pretty expensive endeavor, not just in terms of hardware and money, but also in terms of man hours and oversight. It's tough. If you want a taste of what it feels like, Meta AI actually, when we were training the Galactica model, along with the code, we also released the run book for that model. So, that's a very interesting read to see like what are the many pitfalls that can happen when you're training a large language model or a large model of that size. So typically, you don't want to train your model from scratch, your large foundational model. You want to take something that exists and then modify that or apply that to whatever use case you want to use it for. And that touches upon like a whole family of techniques, starting from the very simple, because of the emergent property of in-context learning. That is, the language model has probably never seen that task before, but within the prompt, if you give it some examples of how to do a task, it's going to be able to do it. So that's like the lowest effort, path of least resistance, and that's probably what you want to try first. If it's a simple enough task.
Would you call that prompt engineering?
Yeah, prompt engineering.
Cool.
It's prompt engineering or in-context learning. Essentially, you're getting the model to learn or familiarize itself with a new task and then just get it to perform on that. And that's pretty effective. It's more effective in the larger foundational models because, intuitively they have more parameters to encode those that sort of information, maybe that nuance in the proposed engineering in the proposed task in the prompt. So that's like your simplest first step that you probably want to try. Retrieval augmented generation is a really hot topic now. It's like at every conference that I'm going to, I'm hearing about that. There's a whole startup cottage industry around this, and it's a pretty cool way to use language models. And I can perhaps explain that in an example with an analogy, somewhat anthropomorphized. So imagine you were tasked with, someone asks you a question, and Brian, you studied linguistic philosophy, so you're clearly an outlier. But let's say someone asked either Randall or me about Wittgenstein. I have no clue. So, but I do know that the library has certain books, most likely has books on Wittgenstein. So that's where I head. I go to the library, I look up the index of topics and find out which shelf would linguistic philosophy be most likely in. I make my way to that shelf. I scan the books and I see, okay, yeah, this title sounds like it might have the answer I'm looking for. And I collect like 5 books, let's say. And I go through all 5 of those books. I find out what part of that book corresponds to what I'm looking for, extract that out, and take notes and write it down. And then I have my answer, even though I knew nothing about Wittgenstein before. And I didn't take a class on linguistic philosophy. I didn't need to, because I had a library, at right here. And that's literally what retrieval augmented generation, or RAG or RAG, does. Your language model does not need to have been trained on that particular data or on that particular topic. But as long as that data is available for it in an index, it is able to go and look it up and find the specific relevant parts of that information and bring that back to you, synthesized in a very nice paragraph, and as if it always knew about this.
I think that's a fantastic way of explaining that. You said something, by the way, that really resonated with me, and it kind of just unlocked a bunch of ideas in my mind. So you said that I'm gonna briefly restate something that you said earlier. Prompt engineering, few-shot learning, in-context learning, and retrieval augmented generation, they are more effective in the larger models because they have better context. They have more parameters upon which to draw upon. But then fine-tuning, you can get results perhaps for specific tasks faster with the smaller models, or at least lower cost of training.
Because they're smaller? Because they're... Yeah, now that's a really interesting point. And actually, it's a really cool segue into what I was going to share next. Because again, kudos to the research community and the open source community. They figured out a way to train your large models, but as if you were training a small model. And when I first read about it, I was like, hold up, like what's going on over here? Because traditionally, I've always thought of fine-tuning a large model as, retraining or, trying to optimize all of the parameters or a large section of the model towards a new data. But with parameter efficient fine-tuning, you're able to introduce a small set of parameters and just train that. And magically, your large model starts to behave as if it has been fine-tuned.
Right, and I think that also can alleviate the whole issue of catastrophic forgetting that large models can suffer from if you overtrain them.
Oh yeah, I mean, not just that. The fact that you are able to modularize these fine-tuned models, it's basically like you have modules of fine-tuning, which you can just attach to a language model, and when you're done with that, you take that out and you switch it up. So for example, let's say I have Llama 2 and I have 2 different use cases. One where I wanted to sound like a professor, he's like a science professor, so he talks in a very certain style. And the other application I have is to sound like a clown, for example, and quite often they both are mutually exclusive. They're quite different very often. But I don't need 2 different Llama 2 versions for it. I can have the same Llama 2 model and I can just plug and play different modules into it. And depending on which module I'm plugging in, it's going to generate output differently.
And are these what are commonly referred to as LoRAs, like low rank adaptations of large language models?
Yeah, these are the adapters, the low rank adaptation, different versions of adapters. It's like part of this family of parameter efficient fine-tuning techniques, best.
We had a debate on a previous episode about the pronunciation of PEFT. Is it peefed, puffed, PEFT? Anyway, sorry, stupid joke.
I was attending a talk by Sebastian Rashka of Lightning AI. So they have a really nice library called Lit GPT, and I really like the abstractions over there for fine tuning your language models. They also support a lot of different language models. But what I was really struck by are some of the benchmarks that he showed. To fine tune a model, like in the traditional way, you would probably need 8 A100 GPUs. But when you're using PEF, you're just using one GPU, and that's all you need to train your model. So that's a direct 1/8 reduction of memory and hardware infra that you need to train a language model. And the output quality is barely differentiable. Like you can't tell that this was not fine tuned in the traditional sense of attacking and changing all of the parameters. It's just taken one very small subset of the model and trained that, and the difference is barely noticeable.
So I'll give one example that we've done at Kalen for one of our customers, and I'll have to be slightly vague about this, just given the nature of the customers. But we had a customer where they did not want to pay the inference cost and the tokenization cost of translating natural language into SQL on a serverless inference style. So we took a Llama 7 billion parameter model, Llama 2, and we gave it through a LoRa a number of examples specific to their schema. And we were able to get great results. And we were then able to additionally quantize that and get it to run very efficiently on an Inf2 instance from AWS. Now, the question there is, what happens if you fine tune too much? So we talked about catastrophic forgetting. Brian brought that up, but I'm curious, how do we avoid overfitting, and what is catastrophic forgetting?
Okay, what is catastrophic forgetting? Essentially, you train it on a new piece of information so much or so long that it forgets the information that made it who it was. Not to anthropomorphize again the model too much, but essentially the model learns by fitting to a certain pattern of information that it has been trained on. And this is your foundational model. And now you take that and you apply it to a very specific downstream task, which might have a much narrower scope of new information. But if you do that excessively, the model has a limited memory in the sense of how much its parameters can encode. So at some point, it's going to not have enough memory to keep or capacity to hold the information it was pre-trained on, as well as the new information that it's being fine-tuned on. So it's going to try to optimize to what the new information is, to remember the new information at the cost of the old information. A very ultra simple example would be like, it has been pre-trained on a statement like the sky is blue, but when it has been fine-tuned, it's going to encounter the sky is red so many times that internally it's going to be rewarded for saying the sky is red more than saying the sky is blue. So in that sense, it has forgotten that the sky is blue is a valid output. That's a very, very that's an oversimplification, but
well, if you want to do an anthropomorphization, again, I think of this as the case of a true believer. Many of us, if we get into a thing, oh my God, everything's that thing. I've become a vegetarian. Oh my God, let me tell you about vegetarianism all the time. And isn't this a metaphor for vegetarianism? And it's like, okay, cool your jets.
So I have a question. Do you think large models, so the 70 billion parameter one, for example, is that less prone to catastrophic forgetting than the smaller models, or is it independent of the size of the model?
I don't have a clear objective answer to this, but if I had to guess, I would probably think that large models are less susceptible, simply because it's going to take a lot more epochs to for a large model to forget, to catastrophically forget. And you probably are never going to be hitting that many epochs because A, it's too expensive and just so unnecessary.
Gotcha. Now, we're really coming up on time here, so I just want to make sure we have a moment to close everything out. What is next? What are the challenges that we're facing? How are foundation models evolving to address some of the challenges that we're talking about here with catastrophic forgetting and things like that? Address hallucination and address the limited context and speed of of performance. What's next? I feel like you're at the state of the art. You're on the forefront of this. What should we be looking out for?
I mean, like we discussed, there's so many open areas of improvement for large language models. There's so many challenges, security and just having ethical outputs is just the tip of the iceberg. And then there's so much going on under it. But if I had to just step back and think about it, I'm just thinking about performance in the sense of efficiency of the operations, but also performance in the sense of what is the quality of the outputs. So on the performance, engineering performance side, I think that there's we're trying to build models which are more robust to model compression. We are building models which are quantization first. They're running with less memory footprints. They have a better context length. It sort of intersects with the quality performance as well. Something that language models today are pretty challenged by is how easily can they incorporate new information. And I'd expect that to be an area of immediate improvement. I think there's a lot of work in that space. How do we help language models incorporate new information? And then, of course, there's always going to be the leaderboard ranking game that folks are playing. There's always going to be a new model that beats the current state of the art. And I think there was one released just a week or 2 weeks back, Persimmon, an 8 billion parameter model, which also claims has a claim to state of the art performance. You also see different techniques coming up. Like there's this whole family of hey, how do we reduce memory footprints? But how do we also get the model to perform better or give us better outputs? And I think I was reading about speculative decoding, which seems pretty cool. So we are probably going to see models which natively incorporate such techniques, probably natively incorporating RAG style retrieval. And then of course agents. I think after language models which are generating languages, you're going to start seeing models which are generating actions and the outputs from those actions. So it could range from, just going onto the internet and fact checking its output, or it could go on to, connecting to the cloud and doing certain tasks and just giving you updates on that, and then coming back to you with the final output. So I think we're just starting. Like we are starting to explore capabilities that large-scale models provide to us. And so far we have only been speaking about the text modality, but there's multimodal models just around the corner now. Models that can understand audio, video, and text together, in a common unified way. I think those are going to be very, very impressive, and they're going to be pretty powerful in what they are capable of.
Fascinating. This is so exciting. I think it's a really fun time to be a part of this industry. I want to give, Suraj, do you have a plug that you want to put in here at the end of the show? Anything you want people to check out?
I mean, I really hope that this conversation may have inspired you to check out Llama 2. Like I mentioned, it's open source, so there's like a whole community around it. There's many different tools, many different applications that can allow you to play with Llama 2. And I think the best way to get a sense for what these models are capable of are literally by playing with it. I mean, language models became such a common parlance because of ChatGPT and because of that whole interface. So please do try to play with it. There are many tutorials and guides on the Llama 2 repository to some extent, but also on Hugging Face, on LitGPT, like I mentioned, which allow you to try out these techniques that we spoke about, PEFT, and even in in context learning or prompt engineering on these models. Try it out on your data, try it out on stuff that you care about, and it's most likely that it's going to leave you a little awed, at least. There's some awe, even if it's even if there might be a world, you might feel a lot of different things, but awe will definitely be one of them. So play with it. That's my plug, I think.
That concludes our episode of Neural NebulAI. We hope we leave you with something to think about as you pursue innovating with AI. If you enjoyed the show, please leave us a rating and review on the platform you're listening to. And don't forget to subscribe so you never miss an episode. Thanks for listening, and we'll see you next time.